Hello, Tensor friends. I was watching this video this morning because I thought it was cute. It's how to derive the area of a circle using calculus. And this is 10 minutes long. It went on and on and on and on. And I thought to myself, goodness gracious, you have to know all these trig identities and all these and substitute them back in. I can do this in a half a page with Tensor the calculus. And your first response is, well, you can't teach tensor calculus to kids. And my question will be, why not? It's no more complicated than this 10 minutes to derive pi r squared. Let's take a look at it. Okay, so we just got a circle here. Its radius is 1. We have a position vector, right? And that position vector sweeps around this circle as a function of the angle of theta, right? So it sweeps out an arc length. So that's what we're going to look at. Okay, so here's my proposition. Derive the area of a circle using tensor calculus. This seems like shooting an ant with an elephant gun, I realize. But it's so simple, my God. So here is the infinitesimal arc length equation. And your first response is, well, you can't teach the metric tensor to children. Why not? This is just the dot product of the basis vectors. The basis vectors are just the first derivative of the position vector. So if they've had the differential, the calculus, which the little guy was using in the video I show, it's the same. It's the same. The calculus. There's no difference. So I would argue that this is a heck of a lot easier than watching that video. Okay, so we have this in polar, the coordinates, this line element, it's called the line element, is the ds squared equals dr squared plus r squared d theta squared. So this is the gij, the grr, the component of the metric, the tensor here is 1. The g theta is r squared. We take the square root of both sides. Now we want to, on that diagram, we had that position vector was sweeping out that entire the circle as a function of theta, right? So we want to differentiate with respect to theta. And since r is not a function of theta, this is 0, d theta is 1. So we're just left with ds d theta equal r. We take d theta to the other side, integrate over that whole path, right? That position vector went all the way around. So that's 2 pi, so we get this. That entire arc length is 2 pi r, which you knew because that's the circumference. Well, now, let's go back and look at the diagram real quick. Okay, so to calculate that arc length, we were holding r constant and sweeping all the way from 0 to 2 pi. But this time we want to integrate r from 0 to the end of the position, the vector, right? To get all of this area in here. So that's the point of the piece. Okay, so to find the area, we just integrate the arc length, which is this, from 0 to r, right? So as r, it sweeps out that entire, the part of the circle from 0 to the end is 0 to r. We integrate this from 0 to r and we get pi r squared. So that is so easy. This is so easy compared to doing it with trig identities and all that stuff. So I think that they could learn tensor calculus a heck of a lot earlier than it's taught because, first of all, it's usually not taught. And second of all, if it is, it's from the physics department. You don't see it to get to grad school. Anyway, that's my 2 cents. I'd like to know what you think.